Okay, so we will look at acids and bases and neutralization for a moment. We introduced acids and bases as one or two of the three types of electrolytes, but now we're going to view them a little bit differently. An acid is a compound that will increase the concentration of hydrogen ions in water. And so hydrogen chloride or hydrochloric acid, when placed in water, will dissociate completely to form hydrogen ions and chloride ions. And a base is any compound that will increase the concentration of hydroxide ions in water. So sodium hydroxide will dissolve in water to form sodium ions and hydroxide ions. So by that, extending that logic, you have a combination of acid and base. When combined, they undergo what is known as neutralization. So they react with each other to form water, right, from the combination of hydrogen ions and hydroxide ions, plus the ionic compound or the salt that results from the cation from the base and the anion from the acid. And then those acids and bases can be categorized into two types. You either have strong acids, which mean that they ionize completely, and you do need to be familiar with those 7 strong acids. So basically the hydrogen halides, with the exception of hydrogen fluoride and nitric acid, perchloric acid, perchloric acid, and sulfuric acid. Weak acids, or any other acids, they will partially ionize in water. So most acids are weak. The 7 strong ones are the only ones that ionize completely. Strong bases ionize completely in water, and those are all the metal hydroxides. And then you have weak bases which partially ionize in water. We're using the Arrhenius definition, which is that an acid is anything that produces hydrogen ions, a base is anything that produces hydroxide ions. And these definitions are limited to aqueous solutions. We do have another definition that is also useful, which is called the Bronsted-Lowry definition, which is that an acid is anything that donates a proton, which is a hydrogen ion, right? If you recall, hydrogen only has 1 proton and 1 electron, so if you have hydrogen ion, it's just a proton, same thing. And a base is anything that accepts a proton, so then that allows us to include ammonia as a base. Here are some common acids and bases that you'll be coming across, and then these are the molarities that are obtained in a concentrated solution. In terms of reactions, we know that non-metal oxides in water form acids, metal oxides in water form bases, and you would be able to write and balance those equations. Again, Bronsted-Lowry definition. There is one more definition which is not quite so useful for us at this stage, but there is a Lewis definition which extends into organic chemistry, which has to do with viewing acids and bases in terms of accepting or donating a pair of electrons. The pH scale is going to be very important, so please familiarize yourself with it. It is a scale from 0 to 14. From 0 to 14. A pH is the power of hydrogen. That's what the P stands for. pH is a logarithmic scale where you calculate that value by taking the negative log of the hydrogen ion concentration. So, at the one end, where you have a pH of 0, is where you have a very acidic solution. In the middle, pH of 7 would be neutral, and then on the other end, pH of 14 would be very basic. Just keep in mind that the more acidic the solution, the lower the pH value. The more basic the solution, the higher the pH value. So, just to give you an idea of some common acids and bases, if you think about your stomach acid, Your stomach produces hydrochloric acid to assist with the digestion of protein. Your gastric juices, or your hydrochloric acid in your stomach, is between 1 and 3. Lemon juice would be somewhere around 2. Soda, somewhere around 2.5. Coffee, closer to 5. Pure water, right around 7. Your blood, slightly basic, right above 7. Milk of magnesia, which is used to neutralize stomach acid, it's about 12.5. Ammonia, which is used for cleaning glass mostly, it's about 12. And then on the extreme, if you had lye, sodium hydroxide, that would be about 14. Another thing to be aware of, and also to understand where these numbers are coming from, is the autoionization of water, meaning water molecules by themselves react with one another to form ions. This happens in very small quantities, such that in pure water you have 10 to the negative 7 concentration of hydronium ion, which is hydrogen ion, and a 10 to the minus 7 concentration of hydroxide ions. So K value, which is what we call the ionic product for water, is the product of those two, which is going to give you 10 to the negative 14 at 25 degrees Celsius. Just keep in mind that water does not appear in your equilibrium constant calculation. So that's why you get this value, and then that's where the pH of 7 comes from. Because if hydrogen ion concentration is 10 to the minus 7, then the negative log of that value is just 7. So, calculating the pH, what do we need? Well, you need the concentration of hydrogen ions. Hydrochloric acid, we said, is completely dissociated. So, if you have 10 to the negative 3 molar hydrochloric acid, that means you have 10 to the minus 3 hydrogen ion. Negative log of that would just be 3. What about if you had 10 to the minus 12 molar hydrochloric acid? Well, then in that case your hydrogen ion concentration is 10 to the minus 12. So what would your pH be? 12. What about if the pH is 5? Could you give a hydrogen ion concentration? Well, the hydrogen ion concentration is always 10 to the negative pH, so that would mean 10 to the minus 5. pOH, very similar, except now you're taking the negative log of the hydroxide ion concentration. So the pOH is a negative log of the hydroxide ion concentration, or 14 minus the pH. The pOH is 4, the pH value is 10. Those two numbers will always add up to 14. So, if you have 10 to the minus 12 concentration of hydrogen ions, that means the pH is 12. So that makes the pOH equal to 2. What about if the pH is 5? So then the pOH is 14 minus 5, which is 9. Just keep in mind that these systems are helping us to keep track of our concentrations of hydrogen ions and hydroxide ions. The sum of those two values is equal to 14. If you want to figure out if an acid or a base is strong, that will let you know. It will let you know based on the pH value. So if you have 0.15 molar hydrogen ion, negative log of that number, you have to use your calculator in this case, is 0.82. pOH would be 14 minus that number, so 13.18. In the case of a titration, you end up with a titration curve. We'll be spending a lot of time with these, so please familiarize yourself with this. In this case, starting with an acid and adding a base. you would get plot of pH over increments of adding the base until you reach what we call the endpoint or the equivalent point, where you have equal moles of acid and base. That value here will give you the volume of base that was needed to neutralize the acid that you started with.